Okay, so now what we want to do is we want to think about a little bit about what happens when we actually have an AC voltage in a circuit. So if we have an AC voltage, an AC source that looks like Vmax cosine of omega t plus phi, then there are a few things we can say about what happens in the circuit. So first of all, if we have a cosine function source, then the steady state solution in the circuit is also going to be a cosine function. And the frequency will be common. So all of the currents and voltages in a circuit with an AC source will have the same frequency. And this is always true when R, L, and C are constants. And it's way beyond the scope of this class to have L's and C's that are not constant. The maximum amplitude, so what's different? What's different in currents and voltages throughout the circuit is the amplitude or magnitude and the phase. So that's what's going to change. So the magnitude, if we have a circuit with a bunch of elements and we have a source and it's an AC source with a magnitude and a phase, then if we look for currents and voltages elsewhere in the circuit, what's going to be different is the magnitude will change and the phase angle will change, but the frequency will remain the same. So in order to analyze circuits that are AC, remember that inductors, the voltage across an inductor is L di dt. And the current in a capacitor is C dV dt. So if we start writing Kirchhoff's laws and we have inductors and capacitors and we have an AC voltage source, then what happens is we're going to get a differential equation and we're going to get multiple sinusoidal functions. So you're going to have a transcendental equation that'll have lots of sines and cosines. You've then got to go to methods in differential equations when you have an inhomogeneous equation with a sinusoidal function and apply those methods to solve the system. So that's hard, and we don't really want to do that. So in order to solve AC circuits in electrical engineering, what we're going to use is a transformation. And the transformation is based on an identity known as Euler's identity. And so what we're going to do is we're going to realize that in every circuit with an AC source, the frequency is the same for all currents and voltages. So the only thing that's changing is the amplitude and phase. So the goal of a phasor analysis is that we want to transform the circuit where we retain amplitude and phase information, solve it in that way, and then transform it back into a time domain circuit. So I'm going to illustrate all of this. I'm just trying to set the stage so that you know kind of what we're doing. All right, so this little relationship right here, e to the plus or minus j phi, or j theta, is the cosine of theta plus or minus j sine of theta. So it depends on the sign, sign, of the exponent. So this is referred to as Euler's identity. You almost always talk about it with the plus sign, and you let the negative sign be incorporated into the angle, but you can certainly write it this way. So you'll notice that this is a complex number, and in electrical engineering, the square root of -1 is equal to j. So I always encounter some resistance toward this because in physics and in math, it's always been I. Circuits is typically the first in a sequence of a number of courses that you will take that will use Euler's identity. They all will use j. So the square root of -1 is equal to j. So j is the imaginary. So e to the plus or minus j theta is cosine of theta plus or minus j sine theta. On the left, this is referred to as the polar representation of a complex number. On the right, this is referred to as the rectangular representation of a complex number. So if you look here, cosine of theta is basically the real part of e to the j theta. And that's going to be really useful because, as you know, derivatives of exponential functions generate back the same function. So if we have an equation that's got a lot of derivatives and even integrals of exponential functions, then basically, no matter how many times we take its derivative or integrate it, we're going to generate the exponential function back. So because it's going to be common, we're going to be able to eliminate the exponential function from the equation, solve an algebraic equation, and we were not going to have to do any differential equation solving. So this is important. This is Euler's identity. It's a very important identity. Commit it to memory now because you'll use it repeatedly throughout your coursework in electrical engineering. This is not hard, okay? It's just a complex number. So we can take cosine theta and write it as the real part of e to the j theta. Now remember when I told you that in electrical engineering we base our AC circuit solutions off of the cosine function, not the sine function? This is why. Because the cosine function corresponds to the real part of the rectangular complex number in Euler's equation. All right, sine of theta can be written as script I times e to the j, or operating on e to the j theta, and that means the imaginary part of. So this is why, as I said, we chose to represent to use the cosine function. So if we have some function v of t in the time domain is equal to some magnitude times cosine of omega t plus phi, this cosine of omega t plus phi part can be written as the real part of e to the j omega t plus phi. And using rules of exponents, we can separate e to the j omega t plus phi into two parts, e to the j omega t and e to the phi. Now what you're going to find is that e to the j omega t is going to be common to every current and voltage in the circuit. So what did I tell you was going to change? If we find different currents and voltages in the circuit, the magnitude will change and the phase will change for different variables in the circuit. So that's cool because really that means this e to the j omega t, it's just sitting here running through the calculations. So technically we can't ignore it. So first of all, we have this expression that gives you v is equal to the real part of e to the j phi, e to the j omega t. Now what we're going to do is we're going to pull out this part, the Vm e to the j phi. So we're temporarily ignoring e to the j omega t, and we're temporarily ignoring the idea that we took the real part, and we're going to set v e to the j phi equal to what we're going to define as a phasor voltage, which when I write it, I'm going to put this little squiggly over the voltage to indicate that it's a phasor representation. And what happens there is the time variation is gone. So we're going to take advantage of this to do all of our calculations, and then after we're totally done, let's look at what, once we have an answer, we will be able to take the e to the j omega t, plug it right back in, and take the real part and get our cosine function back. So here is our phasor transform. This script P means we're going to do a phasor transform on this function that contains omega t. When we have t as a variable, we say that this is a function in the time domain, meaning t is the unknown, and if we were to plot this voltage inside these squiggly brackets, t would be the axis we would plot the variation on. So we call that time domain. Once we do the phasor transformation, look at what happens. The cosine goes away, the real went away, the omega t goes away. We're now in exponential form. So it is Vm, which is the magnitude, e to the j phi. Now, you don't have to actually learn or understand any of the mathematics here. It's nice if you do. All you really have to do is realize that the magnitude of the phasor was the magnitude of the cosine function. And the phase of the phasor was the angle, the phase angle in the cosine function. And then you just plug it in. Now, using Euler's relation, this expression on the previous page, e to the j phi, we can use Euler's identity to expand that into cosine phi plus j sine of phi. The Vm is the magnitude, it just multiplies along. And so now we have a complex number in what we refer to as rectangular form. There is a shorthand notation that's used in electrical engineering when we have a magnitude or an amplitude times e to the j phi. We express that as a angle phi using this angle sign. So all this is shorthand notation for the exponential. So there are some kind of useful things that we'll find out. For example, if you multiply two phasors together, so you have, let's say you have A angle phi and B angle theta. When you multiply those two together, the magnitudes will multiply, so you would get AB. The phase angles will add because they're up here in the exponent, so you would have angle phi plus theta. So polar form or phasor form is given like this is useful to use when you are multiplying or dividing complex numbers. Rectangular form is more useful if you are adding or subtracting. So if we're doing addition, you want to take this polar form, you want to convert it to rectangular form as shown in this expression, do the addition, and then convert it back. Now the inverse phasor transform is if we have something as a phasor, we can convert that, and we do that by adding e to the j omega t back, by taking the real part, and it goes right back to the time domain. So you take the magnitude, plug in, you take the phase angle, you plug in, you plug back in e to the j omega t. So this brings up an important point. If you're working a problem in the phasor domain, and you're given all the variables in the phasor domain, two things have to happen in order to convert back to the time domain. First of all, there needs to have been only one frequency for a source. So you can't have one source that is 60 hertz and another source that is 120 hertz. That would give you two different frequencies. So the frequency has to be, for AC phasor analysis to work, it only works for a single frequency, one at a time. The other thing is it plugs right back. So you would also have to know the frequency. If you don't know the frequency, you cannot go from phasor domain to time domain because the frequency information is not contained in the phasor. Okay, so here's an example of how to add cosines using phasors, and I'm actually not going to do the solution using trigonometric identities because I don't want to introduce confusion. So what I'm going to do is show you how to do this using phasors. The reason this resource has a part A and a part B is they wanted to demonstrate to you how difficult it would be to do this using part A and how much easier it is using part B. So I'm going to ask you to just take that on faith because I want to show using the phasor concept. So the first thing we're going to want to do here is we're going to want to convert these time domain functions to the phasor domain. Now that we've sort of been through the theory behind this, this is very simple and straightforward. We don't have to do anything except say this phasor will be 20 angle minus 30 and this phasor will be 40 angle 60, and then we add them together. Okay, so here, this is what I'm saying. You don't actually have to do all of this because we've already talked about why this works. So, and I will say they have forgotten in this calculation, this example, this is actually e to the j omega t. Basically, you can ignore everything except here's your 20 angle minus 30. Here's your 40 angle 60. And now what we need to do is you need to take each one of these terms in the polar form and you need to convert it to rectangular form. So hopefully they do that in this example. Yeah, so here's our 20 angle minus 30 and our 40 angle 60. So once again, let me just go over, okay? This stuff is not necessary because we've already told you, we've already defined for you how to do the phasor transformation. So you can go straight from this expression for y to this expression for y1 plus y2, the phasor. So how you get from 20 angle minus 30 to this expression 17.32 minus j10, this is where you took 20 times the cosine of minus 30, that's 17.32. You took 20 times the sine of minus 30, that's 10. You multiply that by j because this term is minus j sine of theta. And then you do the same to the 40 angle 60. The real parts add, the imaginary parts add algebraically. You're left with a complex number in rectangular form, and then you just back convert that to polar form. So I want to talk some more with some more in-depth examples of how to get from here to here. I believe on the introductory video I did talk about that and demonstrate it some, so you should already have some examples on how to do that. But what I want to focus on in this lecture is that from here to here, and once again they're just doing a really bad thing here because they have just neglected, there is a T here, okay. So that's just a print error in the textbook. So they take this number in phasor form, they take this phasor, they take the 33.43, and this is your e to the j phi, this is your e to the j omega t, this is your magnitude, taking the real part of that and applying Euler's identity and realizing that the product of two exponential functions is the exponent of the two exponentials added. So it'll be 33.43 plus omega t, all of that times j. Take the real part and you end up with an expression in the time domain. So this is known as taking the inverse phasor transform. So really this is fewer steps than if you have a bunch of trigonometric functions and you have to use the sum and difference of angles formula in order to simplify it. So much easier to work with exponentials than with transcendental functions. Okay, so I want to stop here because at this point I want to give you some practice problems on how to convert from time domain to phasor domain and how to find RMS. So I will continue. The videos will all be posted, but at this point, before you go on, you should be sure that you understand how to convert back and forth and how to find the RMS, various things. So I'll post some problems on that, and you can work those, and I suggest doing that before you move on and listen to the videos on passive circuit elements in the frequency domain. I'm gonna continue to refer to this as the phasor domain because actually frequency domain means something different in circuits too, and filters and electronics. So and you notice here in the text the author uses phasor domain as well. So we'll end the video here and pick up with passive circuit elements in the next video.